All right. This is going to be the lesson on related rates. This is page 137, and it says at the top of the page, implicitly differentiate the following formulas with respect to time. State what each rate in the differential equation represents. So implicitly differentiate is what we have just been doing, and it just means that we take the derivative like usual, except when I come to a variable that isn't what I'm taking the derivative with respect to, then I have to use the chain rule. So here it says I'm going to implicitly differentiate with respect to time. So that means that I'm going to be finding d over dt of some expression. So I'm taking the derivative of something with respect to time. T is going to be my variable. So any time that I'm going to hit a variable that is not t, I'm going to have to implicitly derive like we were doing in the lesson recently. So I'm starting with number 1 here. It says area is equal to 4 pi r squared. This is the surface area of a sphere. When I take the derivative, implicitly you take the derivative of both sides. So let me just rewrite that first. Area is equal to 4 pi r squared, and then I take the derivative of both sides. The derivative of big A is d big A dt. All right, you can think about it like if I cover this up, so it's the derivative of hand is just 1 and then times the derivative of A with respect to t, which is dA dt, and I just don't have to write that 1. So the derivative of A is just derivative of A with respect to t. All right, it's just like what we were looking at before with like dy dx kind of stuff. All right, now here, r is my variable. 4 pi is just a coefficient of that, so the derivative of 4 pi r squared is 8 pi r to the first, I don't have to write that, and then times the derivative of r with respect to time. Okay, so we're implicitly differentiating real-life situations in this lesson, and so we want to explain what each of these things means. And we know that derivative is a rate of change, right? So dA dt is the rate of change of the surface area with respect to time. All right, and then dr dt is the rate of change of what? All right, we're talking about a sphere, so a ball, and we know we have the area of that sphere, or the surface area of that sphere, and then r, then, in these instances, is going to be the rate of change of the radius. R is going to be the radius of the sphere with respect to time. Okay, so the next formula is the volume of a sphere, which is volume is equal to 4/3 pi r cubed. Taking the derivative of both sides with respect to time, the derivative of v with respect to time is just dv over dt. The derivative of this side, r is your variable, so you're going to multiply 3 times 4/3 and just get 4 pi r squared, and then times dr dt. dv dt is the rate of change of the volume. And dr dt again is the rate of change of the radius of the sphere. In the third problem, this says a is equal to the square root of c squared minus b squared, where c is constant. I want this to kind of look familiar to you. If I square both sides here, I get a squared is equal to c squared minus b squared, which is a form of the Pythagorean theorem. All right, a squared plus b squared is equal to c squared is the Pythagorean theorem. And in this form, this is going to be a lot easier to take the derivative of than this, because here I would have had to use chain rule, and now I don't have to do that. Remember, these are equations now, so I can square both sides. Okay. So now I'm going to take the derivative of a squared is equal to c squared minus b squared. But they said c is constant, and that's important. That means that c is just like 5 squared, and the derivative of a constant is going to be 0. So you're going to want to pay really close attention when are you given a derivative of, or when you're taking the derivative of a constant. So a squared, the derivative of that is 2a, and then since that's not a t, we put dA dt. And in related rates, we never really have a t, so dA dt is equal to the derivative of c squared. Well, c is a constant, so the derivative of any constant is 0. And the derivative of negative b squared is negative 2b times dB dt. All right, so there's my derivative, and dA dt is the rate of change of A. All right, and dB dt is the rate of change of B. Number 4 is the volume of a cylinder. All right, so we're talking about a cylinder now, where R, which is going to be the radius of that cylinder, is going to be constant, and the H is going to be a variable. So V is equal to pi R squared H. And again, R is a constant here. That means that the derivative of the left side is dV dt, because volume is a variable. But all of this is just a coefficient in front of that H, since R is a constant. So it's just like a 6. So there's no difference between the R and the pi in the way I differentiate. So all that's just a coefficient of H. So the derivative of that is keep the coefficient and then times the derivative of H, dHdt. All right, and dV dt is the rate of change of the volume of the cylinder, and dHdt is the rate of change of the height of the cylinder. On the next problem, we have a right triangle with the hypotenuse, we have an x, and we have that this is a theta. All right, it's going to be very helpful for a lot of these to draw yourselves pictures. But this is my formula. Cosine theta is equal to x over 15. The derivative of cosine theta, now I'm taking the derivative with respect to t, which means since theta is not a t, I'm going to use implicit differentiation. So I cover up that and I take the derivative of the outside, which is cosine hand. The derivative of cosine hand is negative sine, keeping the inside the same. So negative sine hand and then times the derivative of hand, which means negative sine theta times the derivative of theta with respect to time. The derivative of x over 15, well, this is 1 over 15x, so the derivative is just 1/15th, and then times dx dt. d theta dt is the rate of change of theta with respect to time. dx dt is the rate of change of x with respect to time. And then number 6, the volume of a cone. Here, so I've got V, volume is a variable, 1/3 pi, those are both constants, R squared and H. I'm not told that anything is a constant, and so that means that R and H are variables, and when you're multiplying variables, you have to use your product rule. So the derivative of the left side is just V d dt. The derivative of the right side, I'm going to use my product rule, where this is my U and this is my V. So UV prime plus VU prime. All right, so first times the derivative of the second plus the second stays the same times the derivative of 1/3 pi r squared is 2/3 pi r times dr dt. All right, that was kind of a doozy, so please check that over. So this is our implicit differentiation with respect to time of different formulas, and we're going to keep coming back to this sheet to get the formulas that we're going to be using today. So this paper, or this page right here, shows the tools that you're going to be using for this lesson. It's very similar to what I remember about physics problems, whereas you are given a bunch of information and you're looking for something. So basically, we are going to figure out these first 3 steps of this process here is just figuring out what you're given and what you're looking for. And then we're going to start using the calculus to find it. So I have this chart here just to break down how we're going to think about it. But when you have this problem, I'm looking on page 138, when you have a problem like this, you know, you're only going to be given the word problem. So this is just going to give you a process to go through the problems to try to figure it out. So air is leaking out of an inflated balloon in the shape of a sphere. All right, so imagine you've got a balloon here, you've got a sphere, and it's leaking, air is leaking out. So this sphere is getting smaller, all right? It's getting smaller as time goes on. So what information are we given? Well, first we know again that the balloon is getting smaller. We know that from this first phrase here. We know the rate at which the air is leaving is 230 cubic centimeters per minute, and units are going to be very important here. So this is volume of the air in the balloon, and I know volume because of the context of the problem, and also because it tells me that my units are cubic centimeters, and that cubic units means volume. So I would call this dV dt. This is the rate at which my volume is changing at the instant when the radius is 4 centimeters. So at the instant when something is changing. So over time, this balloon is constantly getting smaller and smaller and smaller. But we're just going to freeze it for a second and look at we're going to study it at an instant in time. The moment when the radius is 4 centimeters, we're going to talk about the rate that the volume is leaving, and then we're also going to talk about the rate that the radius is changing. So at what is the rate of change of the radius? That's the next thing we're going to be looking. And we would call that dr dt. The radius of the spheres r, and so the rate that is changing is dr dt. Okay, so identifying all of the variables that are involved in this problem, well, you've got volume, all right, and you've got your radius. And I will even say dV dt is going to be variable, and then r, and then dr dt. All right, that's all the different information that I'm given. Identify which, if any, of the variables in the problem remain constant. So that means, is the volume or the radius going to stay the same as this balloon gets smaller and smaller? And it won't. All right, so we have no constants in this situation. As time goes on, both the volume and the radius consistently are changing. Okay, identify the rates that are given and the rate at which you wish to find. This is really the most important to set yourself up, because you're again identifying what are you given and what are you looking for. So we have all of the variables listed, but we're going to actually give the amount for each one of them. What was the rate of change of the volume? Air is leaking out of the balloon at a rate of 230 pi cubic centimeters per minute. So we know that rates can be positive if something is getting bigger, or a rate can be negative if something is getting smaller. And so because the air is leaking out of the balloon, and so the volume is getting smaller, this rate is actually negative 230 pi cubic centimeters, so centimeters cubed per minute. You want to be very careful about your positive or your negative rates, because that can definitely mess you up if you miss that. And then at this instant in time, we're told that the radius is 4 centimeters. And we're looking for dr dt, the rate of change of the radius. So that's my unknown. I do know the units there. I'm going to go ahead and find my units. All right, so if the volume is a cubic centimeter per minute, then the radius is just a plain old centimeter. And of course it's a rate, so centimeter per minute. Okay, step 4 says write an equation, often a geometric formula or trig equation, that relates all of the variables in the problem for which the rate is given or for which a rate is to be determined. Substitute any value that represents a variable that is constant through the problem. All right, so we'll come back to all of the small print here, but right now in this next step, you have to come up with the equation that relates all of these things. And so here we're talking about the volume of a sphere, And so we were given that. We go back to page 137. The volume of a sphere is pi, where am I? Volume of a sphere, excuse me, 4/3 pi r cubed. All right, so this is the volume of a sphere. And then I can jump down to step 5 because I don't have any, in a few different examples, we will have to do more information here, but right now, that's good to go. We are ready to go to step 5, which means implicitly differentiate both sides. So dv dt is equal to the derivative of this side. R is your only variable, so it's 4 pi r squared dr dt. Okay. And then at this point, we are going to substitute all instantaneous rates and values of the variable and solve for the remaining rate or variable, and we're going to include units. Write that in, please. Okay, so we are given dv dt. We are given r in this instance, and we're going to find dr dt. So that's what should always end up is where you have an equation and you've got everything you possibly need except for the one thing they're asking for. Now sometimes it's going to be a little bit more complex where we have to do some stuff to find those other things, but right now you're given this, and you need to find that guy. So it's just algebra here. Let's plug in. dv dt was negative 230 pi is equal to 4 pi times r is 4 squared dr dt. 4 squared is 16 times 4 is 64 pi. And I can divide that on both sides and get negative 230 pi over 64 pi is equal to dr dt. I do not have to clean this up if it's a free response, but the pi's will cancel out, and if I wanted to get a decimal answer for that, because sometimes these are calculator problems, this would be negative 3.594. Now we want to include our units, which we had found earlier, centimeters per minute. Okay, next problem. A stone is dropped into a calm body of water, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So here you've got a pebble got thrown into water, and it is creating concentric circles. And we're looking at the outermost ripple in the water. So, what do we know? All of the variables, let's see, the radius is increasing, so since it gives me that it's increasing at a rate, that means that is the dr dt, all right? I'm given the rate of change of the radius. When the radius is 4 feet, that gives me, at this instant that I'm going to look at, that's when the radius is 4 feet. At what rate is the total area of the disturbed water changing? So that would be, I want to know the rate of change of area. So that's going to be dA dt. And so this is the image that I'm thinking of, all right? Remember, it's creating concentric circles. And so I'm going to look for the area of a circle. So I need to know the area of a circle formula. And area formulas are not given to you on the test. Volume formulas are given to you, but area formulas you need to know. So nothing in this situation remains constant. All right, the radius is always changing. The area is always changing of that circle that we're looking at. So we, again, have nothing that stays constant. Identify the rates that are given and the rate that you wish to find. So again, I'm just going to take these guys and I'm going to put values to them. dr dt is, now this radius is getting bigger, so that means that this is going to be a positive 1 foot per second. All right, again, I know that r is going to be 4 feet at this instant in time, and I'm looking for dA dt. I want to go ahead and think about my units for dA dt. Since this is going to be the area of a circle, these are going to be square units. So square feet, and it's a rate, so it's still over times seconds. Be careful, don't accidentally switch seconds to minutes, because you could have everything correct, but you will not get your units point if you make a careless error and call your seconds your minutes, or feet your meters, or whatever. Okay, so what equation relates radius and area of a circle? That would be area is equal to pi r squared. And again, you have to have that memorized. That is not going to be given to you. Okay, you can take the derivative of both sides now. dA dt is equal to 2 pi r times dr dt. Whoops, that was supposed to be step 5, to take the derivative. And then substitute everything you know. So we are looking for dA dt, so we're going to find that guy. We are given r, and we are given dr dt. So just plug in everything you know. dA dt is equal to 2 pi, that's a constant. R, we're told, is 4 feet at this instant, and then dr dt is 1. So this is 8 pi, excuse me, square feet per second. And now we have found the rate of change, or it says, remember, go back to the question, make sure you found what you need. It says, at what rate is the total area of the disturbed water changing? And so this is the rate of change of the water. And it's positive because the area of the circle is getting bigger. Okay, on the next problem, we have water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. So we've got a cylindrical tank we're dealing with here. Water is leaking out of this. So then there's water inside here, and it is draining out of this, or leaking out of this tank. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? So we know that water is leaking out at a rate of 3 cubic feet per second. And again, looking at cubic feet here, that gives me a clue that this is going to be dV, change in volume over change in time. Also, because this is water leaking out, the water is getting smaller. This is going to be a negative rate. I just want to make myself a note about that. If the radius of the tank is 4 feet, okay, as the water leaks out of this tank, is the size of that tank ever changing? This is a tank with radius 4. The size of that tank is never going to change, and the size and the radius of that tank is the same as the radius of the water in the tank. So in this case, we're going to have a constant, and we're looking for at what rate is the depth of the water. We're going to call the depth of the water h, because that will relate in our formula better. So we're looking for the rate of the water changing. So we're looking for dH dt. So we know that the variables involved are volume, radius, and the height of the water. We know that the radius of the tank, and the water, right, because the water assumes the same shape as the tank, will always be 4 feet. And water. Okay. So I'm just going to start listing everything I'm given. dV dt is equal to negative 3 cubic feet per second. The radius is 4 feet. I'm looking for dH dt. And the units of dH dt, since this is just a linear unit and it's not area or volume, this is just going to be plain feet per second. And now we talk about what equation will relate all of these things. And so we want the volume of a cylinder, and that is volume is equal to pi r squared h. And so it's very important here that we recognize that R is a constant. All right, rate in this situation, in this tank, the rate is going to be a constant, which means it's just like, you know, well, again, it's 4. So 4 is no different than 3.14. So this is all just a coefficient in front of H. So I'm ready to go on to step 5. In the next example, we're going to talk about where R and H are still both variables, and that's when we're going to have to deal with some of the other stuff that was talked about here. But at this point, I'm ready to take the derivative. So dv dt is equal to pi r squared, pi r squared, because that's my coefficient, times dh dt. All right, and at this point, figure out we are given dv dt, we are given the radius, and now we can find dh dt. So solve. And so that's 16 pi, so negative 3 divided by 16 pi, and then what will my units be? Feet per second, because I had already figured that out up here, is equal to dh dt, which again, they said, what is the rate of the depth of the water changing? So this is the height of the water, or the depth of the water is changing at negative 3 over 16 pi feet per second. All right, at this point, I need you to look at your fraction here and make sure, so like if you have this is not an acceptable form of this answer because that pi is not clearly in the denominator. All right, so I need you to stack your fractions vertically here and make sure it is very obvious that that pi is in the denominator. All right? Because you do not get the benefit of the doubt with presentation errors. Like I would assume that that's being multiplied if it was not clearly in the denominator. Okay. The next problem is a cone problem. It says a cone has a diameter of 10 inches and a height of 15 inches. So we've got a cone, and it says water is being poured into the cone, so I know that this is an upward facing cone. All right, with a diameter of 10 inches and a height of 15 inches. Water is being poured into this cone so that the height of the water level is changing. All right, so water is being poured into the cone, and this is my water being poured in. And so I have a cone inside the cone of the water. And the height of the water level is changing at a rate of 1.2 inches per second. And since the water level as it's being poured in is going to grow, that means that this is a positive rate, and I'm going to call that the height of the water, so I'm going to call it dH dt. All right, so I know the rate that the water is growing, the rate that the height of that water is growing. At the instant when the radius of the exposed, that should be exposed surface area of the water is 2 inches. So the exposed surface area, if you look inside this cone and you're looking at just a circle of water, all right, so the radius of that exposed surface is 2 inches at this moment in time that we're going to look at. What is the rate of the volume of the water changing? The volume of the water. So I'm not being asked about the volume of the whole cone. I'm being asked about the volume of what's changing. Okay, so all the variables involved in this problem, well, you have the diameter of the cone. You've got a height of the cone. You've got a dH/dt, you've got R is 2 inches, and you've got dV dt. So everything I underlined here, and then drew your picture of here. Okay, what remains constant here is your big cone. So that's not what we're really looking at. We're looking at how the cone of water is changing, but as the water grows, the height of the water will change, and the radius of that exposed surface will change. We're just going to use that big cone to help us solve. Okay, so I want to list everything out. let's see, dH/dt is 1.2 inches per second. R is 2. dV/dt is what I do not know, and it's volume, so it's going to be cubic inches per second. Okay, so write an equation that relates all of these things. I'm going to be looking for the volume of a cone. So the volume of a cone is V is equal to 1/3 pi r squared h. Okay, and then now is where I'm going to have to look at the small print, what's going on here. If I were to take the derivative of this right now, what I need to end up with is I need dV/dt to be my only unknown, because that's what I'm looking for. And everything else I have to be given so that I can solve for that. So when I take the derivative of this, if I did that right now, I would get dV/dt, which is good. I would get dr/dt at some point, and that's not good because I don't have a dr/dt. And I would be given a dH/dt, and dH/dt is good because I have that. So I do not have a dr/dt. Even though I have a even though I have a radius, I don't have the dr/dt. I don't have the rate of change of the radius. And so what I need to do is somehow change this equation to get rid of that r. I need to make it so that there's no r and there are only h's and v's. And so what I can do is use the fact that this big cone and the cone inside of it are similar figures, right? They're similar figures. You can think about these are similar triangles. This radius of the big cone to the height of the big cone is similar to the radius of the little cone to the height of the little cone. And so the ratio of radius to height is going to be the same since they're similar figures. So the big cone had a diameter of 10 inches, which means it has a radius of 5, and it has a height of 15 inches. So the ratio of the radius to the height of this cone anywhere at any point in time, wherever that water level is, the ratio is going to be 5/15 or 1/3. Right? Now I want to use this relationship, r over h is equal to 1/3, and I want to use that consistent relationship here to get rid of this r. And so I'm going to, again, think of this as a system of equations. If you've got two variables, you need to have two equations. I want to replace that r with h, so I'm going to isolate r here. R is equal to 1/3 h. And now I'm going to plug that back in here. So I'm going to plug in 1/3 h for r before I take the derivative, because I need to get rid of that r so that I don't end up with a dr/dt. So you do this before you take the derivative. So volume is equal to 1/3 pi, and instead of r, I'm going to write that as 1/3 h squared times h. And then I'm going to clean this up. Cleaning it up is the only way that's going to make this really palatable. So 1/3 pi, 1/3 h squared means that the 1/3 gets squared and the h gets squared. So this is 1/3 pi times 1/3 squared is 1/9, h squared, and then times another h. And then that is 1/27 pi times h cubed. And now that's your volume, and now I can take the derivative of that. So let me just start with rewriting it. V is equal to 1/27 pi h cubed. And then to take the derivative, dV/dt is 3/27 pi h squared times dH/dt. And now that I took the derivative, I have dH/dt, which is good because I'm given that, h, which I can find, and then dV/dt, which is my unknown. So again, I said I have to have only one unknown. So dV/dt is my unknown, but I have an h here, which isn't great, right? Because I'm not explicitly told an h, but I know this relationship r is equal to 1/3 h is true throughout the problem. It's true no matter how high the water is. So at any instant in time, the radius is going to be 1/3 of the height. And so at this instant in time, the radius is 2, because we were told that. So then times 3, that means at this instant in time, when the radius of the water is 2, the height of the water is 6. And so plug that in, plug in everything you know, and so this is 3/27 pi times 6 squared times CHGT, which is 1.2. I would use my calculator for this one since they give me a decimal. That often means that my answer will result in a decimal. And so 4.8 pi, or 15.079, and this is volume, rate of change of volume, cubic inches per second. Those cone problems are some of the more difficult problems. So once you've implicitly derived your formula, you always have to be have to know everything except one value, but sometimes those values, like our h, it's disguised a little bit, but you have to have everything you need to solve the problem at that point. So once you take the derivative, you have everything you need somewhere. All right, so on the next page, we are dealing with a ladder leaning against a wall, and we're going to draw a picture here, and the labeling is very important. And so the A, B, and C are all going to deal with the same triangle that we're going to draw. So please make sure for this instant that you label your triangle the same way that I label it, because as my 7th hour will tell you, we definitely had some problems when we were not labeling it the same, when I was not labeling it the same. Okay, I've got a 25-foot ladder leaning up against a wall of a house. So this is my ladder, it is 25 feet. All right, the length of the ladder is never going to change. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Before I can label that, I need to give it a variable. So I'm going to, this is all the information about my triangle that I'm given at this moment. I'm going to label the bottom A and the side B. It doesn't matter if you use different variables in general, but I'm thinking of right triangles, Pythagorean theorem, so I like to use my A's and my B's. But again, for you to understand what I'm doing here, it is important that you match the way I labeled my triangle in this case. If you're doing this on your own, you can label however you want. Okay, so the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So this is the base of the ladder, and it's pulled away from the wall, which means that A is going to get bigger at a rate of 2 feet per second. So that means that this 2 feet per second is d little a over dt. All right, I could think about 25 feet long as being my C if I'm talking about a right triangle. It says, how fast is the top of the ladder moving down the wall when the base of the ladder is 7 feet from the wall? So in the instant that I'm looking at, I know that A is going to be 7 feet. All right, 7 feet from the wall in the instant of time that I'm looking at. What I like to do here is draw myself another triangle and label what this looks like in this instant of time. So 7, 25, and then we can find this other length if we need it of B using Pythagorean theorem. So how fast is the top of the ladder moving? That means we are looking for dB dt. And since the ladder is going down the wall, the B is getting smaller, so this is going to end up being some negative value. I like to give myself a note for that because for me that's a place where I have I have an issue remembering that sometimes. Okay, so the ladder is 7 feet. That was my A and a particular second. All right, so what relates A, B, and C? the Pythagorean theorem. So that's where I'm going to start. A squared plus B squared is equal to C squared. So this is my formula, and now I am going to take the derivative of each of these with respect to time. The derivative of A squared is 2A dA dt plus 2B dB dt. And C is a constant, so the derivative of any constant, I'm actually going to go ahead and put that in as a 25, because sometimes I have a tendency to pretend it's a variable if I don't go ahead and plug in that constant for me. So 25 squared, the derivative of any constant is just 0. So this is my derivative, and now I'm going to plug in everything I know. So 2A, A is 7 feet in this instant, dA dt is 2 feet per second, plus 2B dB dt. dB dt is what we're looking for, so I need B. But we said we could find B in this instant by using the Pythagorean theorem. So I'm going to say 7 squared plus B squared is equal to 25 squared. Solve using the Pythagorean theorem, 25 squared minus 7 squared. B is equal to 24, right? Because that would be 576, so the square root is 24. All right, so plug in. Let me just slide this over here. 2 times A is 7. dA dt is positive 2. Plus 2B is 24. dB dt is my unknown, and that's equal to 0. And so now you have one unknown, and you can solve for dB dt. Remember, B, the height of the ladder against the wall, is getting smaller, so your answer should be negative because that height is decreasing. Let's see. Negative 28 over 48 is 7 over 12. You don't have to reduce. And that is going to be feet, because we're talking about feet, and our time is seconds, so feet per second. All right, so this is my first answer. dB dt is equal to negative 7/12 feet per second. Okay, I'm using the same situation, so I'm using the same triangle that I've labeled the bottom A, the height B, and of course the ladder is 25. Consider the triangle formed by the side of the house, the ladder, and the ground, so the same triangle. Find the rate at which the area of the triangle is changing. So I'm going to call that d big A over dt. It's important that I use a capital A here since I had already talked about lowercase a meaning something different. When the base of the ladder is 7 feet from the wall, all right, so that's important because that tells me that I'm looking, the when is the time that you're looking, and this is the exact same instance as before, so I know that A is equal to 7. I know that B, so A is equal to 7. I know that B is equal to 24 at this time. All right, since it's the same situation as the part A, and it's the same instant of time, I also know that dA dt and dB dt are going to be the same. So A was equal to this, B is equal to this, dA dt is still equal to 2 feet per second, and dB dt is equal to negative 7/12 feet per second. All right, so this is everything that I know, and I'm looking for find d big A dt. All right, so that's my unknown, and the units of area will be square units, so instead of just plain feet, it's going to be feet squared per second. So this is everything that I know and what I'm looking for. And now the area of a triangle is going to be the formula that relates all of these sides. So the area of a triangle is 1/2 base times height. That's how I have it memorized, 1/2 base times height. But I want to use the same variables that I have here. So 1/2 base is A, little a, times height, so B. 1/2 little a times little b. Okay? Both little a and little b are changing. They're both variables, which means that when I take the derivative, I'm going to want to use my product rule and consider this as my, my first and my second factor. So we can take the derivative of the left side is d big A over dt, and then my product rule is first stays the same times the derivative of the second, plus second stays the same times the derivative of the first, which 1/2 A is 1/2, and then times dA dt. Okay, it's kind of ugly, but we have all of this information that we know already, and so when you plug in everything that you know, you should end up with only one unknown. So this is 1/2 times A in this instant is 7. dB dt is -7 over 12, plus B is 24, times 1/2 times dA dt is 2. And so when you do all that out, you've only got this one unknown over here, so there is your answer. All right, so when you multiply and add and do all that fun stuff, you end up with 527 over 24. We said our units were square feet per second. As a decimal, this is 21.958. Remember that you must use 3 decimal places or all your work was for naught. Okay. Find the rate at which an angle formed by the ladder and the wall of the house is changing when the base of the ladder is 9 feet from the wall. So we're still dealing with this same ladder up against the wall, but we did change our instant in time because now we're looking when the base of the ladder is 9 feet from the wall. So I know that A is going to be 9 feet from the wall. In that moment, I can find B if I need it. All right, so right now my triangle is 25. A is going to be, in the instant that I'm looking at, 9 feet from the wall. I also have a new variable here. It wants to know the rate at which the angle formed by the ladder and the wall is changing. So the ladder and the wall form an angle theta here. This means that my unknown, what I'm looking for, is d theta dt. All right? And theta is always, in calculus, it's always radians. So my units would be radians, and then we're still talking about seconds. So it's going to be radians per second whenever I find my answer. I know that A is 9. Let's use Pythagorean theorem to find what B is going to be. So A squared plus B squared is equal to C squared. In this instance, I know 9 squared plus B squared is 25 squared. All right, 25 squared minus 9 squared is 544, which doesn't have a pretty perfect square root or anything, but I'm just going to call B the square root of 544. Okay, when you are talking about an angle, we will now use a trig formula to relate what we know. So we know, and I want to use what they give me, so I want to relate this theta with this side A and the hypotenuse. All right, I could use B, but I generally like to go with what was given, and also B is an uglier number than 9. So I have the opposite of this angle theta and the hypotenuse, and so we need to know that that means that I can use sine. Sine of theta is equal to A over 25. A is, it's still a variable A, all right? We use the variable until the very end. I can plug in at this instant in time, but right now these things are changing, so they're both just variables. And now take the derivative of both sides. The derivative of sine of theta is cosine theta times d theta dt. And the derivative of A over 25 is 1 over 25 dA dt. Okay, we're looking for d theta dt, so this should be my unknown. That means that I need to know what cosine of theta is, and I need to know dA dt. So dA dt is going to, it was given to me in the very beginning because dA dt was how fast the base of the ladder was being pulled away. So that never changed. So that's still 2 feet per second, all right? And then cosine of theta, well, we need to use what we know about our trig formula, our trig ratios. So let me see what we've got here. So 1 over 25 times 2 d theta dt. And then cosine of theta, cosine is the adjacent over the hypotenuse. So in this instant in time that we're looking at, the cosine of theta in this instant of time is the adjacent, which is b, the square root of 544, over the hypotenuse, which is 25. So this is the instant in time. Any instant in times, any wins, those always get plugged in at the very bottom. So now you have everything you need to solve for d theta dt. So d theta dt is equal to, I'm going to multiply 25 on both sides, which will, times 25, which will get rid of that denominator here. And then divide by the square root of 544, so I'm left with 2 over the square root of 544. And I could use my calculator to get a decimal of that, but sometimes this won't be a calculator problem, and sometimes I can leave it like that also if it's a free response question. And this is radians per second. All right. An airplane, here we go, page 143. An airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles past the antenna, the rate at which the distance between the antenna and the plane is changing is 240 miles per hour. What is the speed of the plane? Okay, so we need to kind of understand our situation here. You have some antenna, right? This is going to be my antenna. And an airplane is flying at an altitude of 5 miles above it. So this is my airplane. Let's see. All right. There's my airplane flying directly above this. I know that when it passes over the antenna, this is an altitude or a height of 5 miles. When the plane is 10 miles past the antenna, so the airplane keeps going forward, and then when the airplane gets to be 10 miles past the antenna, right, which means this is 10, and when it says when, that's going to be in the instant of time. So that's going to be at this instant that I look at this. It's going to be 10 miles. The rate at which the distance between the antenna and the plane, so the distance between the antenna and the plane is this distance. You can see that we have a triangle forming here. Since I have a triangle and this looks like it would be the longest side, I'm going to go ahead and call that C. The rate at which the distance between the antenna and the plane is changing is 240 miles per hour. So 240 miles per hour is going to be my dc dt. What is the speed of the plane? Okay, speed or the rate of change that it is moving this way. Okay, so let's give ourselves some variables here. I said this looks like a triangle. I'm going to call that C. I'm going to go ahead and call this length of this triangle, I'm going to call that A. And then this can be my B if I want to think about it that way. But that is going to be a constant. It's going to be 5 miles consistently. Okay, so what do I know? I know that A is 10 miles. I know that dc dt All right, the rate of change of the distance between the two is positive 240. What are my units? This is miles per hour. Okay, we're looking for the speed of the plane, which is how fast is this changing? How fast is it going from point A to point B? So we are looking for dA dt. This is my unknown, and the units are going to be in miles per hour. Okay, so we have a right triangle here, and so what relates all of these is the Pythagorean theorem. Again, I don't even want to necessarily call that a B because I have the mistake of, I make the mistake of accidentally differentiating that, but I'm going to plug in the constant. So my Pythagorean theorem is A squared plus this guy squared, 5 squared, is equal to C squared. And now I'm going to take the derivative of that, 2A dA dt plus 0 is equal to 2C dC dt. Okay, let's see where we stand here. I know that I'm given dC dt. Since this is the instant of a right triangle, I know that I can find any length of the triangles because I'm given A in this instant, which means I can find C. And that will leave only dA dt as my unknown. So I've got everything I need, except I do have to find C here. So let me just go ahead and, all right, so if this is the triangle when this is 5 and this is 10, I want to find what will my C be in this moment in time. So that's my hypotenuse, so C squared is equal to 5 squared plus 10 squared. 25 plus 100, 125, so C is equal to the square root of 125. All right, so I'm going to start plugging things in now. 2 times A, 10, times dA dt, that's my unknown, so that stays dA dt, is equal to 2 times the square root of 125 times dC dt, which is 240. And now you can solve for dA dt. All right, so multiply all that stuff, divide 20 dA dt is equal to 268.328, and make sure you include your units, miles per hour. Okay, let's see. Next problem. A spherical balloon is expanding at a rate of 60 pi cubic inches per second. A spherical balloon is expanding at a rate cubic inches. All right, so I'm told a volume here, dV dt. So I know that dV dt is positive 60 pi cubic inches per second. How fast is the surface area of the balloon expanding? So I'm looking for the rate of the surface area with respect to time. Surface area is going to be square inches per second when the radius of the balloon is 4 inches. Okay. So this is a fun problem because we are talking about volume and area at the same time here. What we know is, so we don't have a formula that relates the volume and surface area together. But what we do have is we can find the volume of a sphere and we can find the surface area of the sphere, and they involve the same units. So let's look at that now. Volume is equal to, and this is just the given formula, 4/3 pi r cubed. Surface area, which I'm just going to call big A. Big A is equal to 4 pi r squared. All right, and these are both from the first page of notes and so we would be given those, surface area of a sphere and volume of a sphere. Okay, these are both in terms of r. So what I can do is take the derivative of both sides. Take the derivative of both of the equations. And then I can solve for dr dt in one of them and use it in the other. I know that sounds a little, or I imagine that sounds a little bit tricky. So what we're going to do right now is implicitly derive both of these separately. So volume dv dt is equal to 4 pi r squared dr dt. All right. Area is going to be dA over dt is equal to 8 pi r times dr dt. So what is good is that, I'm given a volume, I'm given a, or I'm looking for that, I'm sorry. I'm given a volume, I'm given a instant of this radius. I am just going to have to find my dr dt, and then I'm going to plug it in over here. All right, so I need this guy, and so I'm going to use this equation. So let's plug in what we know. dv dt, this was expanding, so these were positives. dv dt was 60 pi. 4 pi, I know that the radius is 4 at this instance. Okay, so here, it should now make a little bit more sense that my only unknown in this equation is dr dt, and I need dr dt here so that then I can solve for the ultimate question, dA dt. So when you isolate dr dt in this case, that's going to be 4 squared times 4, which is 64 pi. So 60 pi over 64 pi is equal to dr dt. Which I can reduce to be 15 over 16 is equal to dr dt. All right, so then I can plug this dr dt in here. So 8 pi r in the same instant is still 4, so I knew that one. And then dr dt, now we know is 15/16, and now I can multiply all of that stuff together and get my final answer of how fast the surface area is changing. So multiply all of that together, you end up with the derivative of the surface area with respect to time is 30 pi square inches per second. Okay, so that is the first lesson. You will need to do the homework before I see you again, and there is a lot. You have to practice a lot of this to get good at it. So please plan to set aside some time to get this stuff done and really focus on it. And we'll be going over questions on Wednesday and Thursday.